what we're going to do now is ask a couple of our panelists to come up. We're going to do a panel discussion moderated by me on Python and research. So maybe those folks who are on the panel can come up. I don't see Chris in the audience, so it may just be 3, which is completely fine. Yeah, grab a seat. And the goal of this is really to introduce you to some people who are actually using Python in their research. And because many of you are transitioning from one language to another, the pattern that we wind up seeing is that you're coming from a lab or at least a research domain where another language is the thing that you learned. That's almost by definition. So one of the things that we're going to try to get out of this panel discussion is understanding of how these folks made the transition, how they wind up interacting still with maybe some of their colleagues who haven't made that transition, and then just get some thoughts on really where things are going in their own research in the context of Python. So I'm going to do some moderation here, but I'll make sure that we have some time for questions. At the end of this panel, we'll do basically a little wrap-up talk where I'll just show you a couple of things that we're going to wind up doing in the broader Python class that now begins on Friday, where we're going into much more depth on a lot of the topics that you saw in the boot camp. So let's get started here. What I'll ask each of the panelists to do is introduce themselves, where they work, what they work on, and maybe just a minute or two about just sort of overall where Python lives within their research scope. So let's start with Clarice, and then we can have you use the mic if you don't mind.
Okay. So my name is Clarice Aiello. I've been a postdoc here at UC Berkeley for 1 year. I'm a graduate of this course last year, and I basically do instrument control with Python at the Molecular Foundry at LBL. And that's something that wasn't, we haven't had time to really discuss that, but there are many Python packages which are very appropriate for controlling hardware and building user interfaces to control instruments and to run synchronized experiments. And
hello, I'm Nel Varoko. I've recently arrived here at Berkeley for a postdoc, so I've been here for 3 months now in the statistics department. I do biostatistics, which involves quite a lot of data science, as we have a huge amount of data, and quite a lot also of statistics. I started Python a while back now, 8 years ago, when I was working in a company. So I also did software engineering before my graduate life, with a lot of C++ and a bit of Python, and then I've been using C++ and Python in my research since I started.
My name is Fernando Perez. I think I've virtually met some of you on the chat room, but I was at another meeting for the last 2 days. I am a scientist at Lawrence Berkeley Lab, and I'm also a researcher here on campus. I'm at the Berkeley Institute for Data Science. And I started using Python back in 2001, before it was kind of fashionable. I was a grad student in particle physics, and I basically was trying to replace sort of a big stack of, in my case, it was C, Bash, Awk, Sed, Perl, IDL, for those of you who come from the physics astronomy world, you may be familiar with it, Mathematica, GNU plot, and probably a smattering of other stuff in my own C and C++ codes and some Fortran here and there with a less complex environment. In 2001, it wasn't obvious that Python was the answer for that, but faced with actually having to work on a dissertation, it was much more tempting just to dive into building tools. That's how IPython was born. I was basically figured that I could spend an afternoon developing that. 15 years later, I'm not doing particle physics anymore. I'm not doing applied mathematics anymore. Really, my work has now become working on the environment itself, on the tools. And so the folks in my group, we work on the building of Jupyter itself, which is sort of the evolution of IPython as a multi-language, multi-platform system for computation in the sciences. And so these days, rather than working on numerical problems themselves myself, I sort of look at the landscape of what is happening in science with these tools and try to continue understanding how can we build a better set of tools for research, which is open, robust, collaborative, reproducible, et cetera.
Great. So Nelly, you said that you're in statistics. When people think statistics and computing, they tend to think the R language. Maybe you could say a bit about your history with R, and then if all of your collaborators are using Python or some are using R, and how you kind of forward that universe.
So indeed, in particular here at Berkeley, I think in the biostatistics department and world, everyone uses R, so I'm a bit of a lone wolf here in my team, but I'm hoping to convert a couple of people to Python. During my PhD, I would say things were a bit different. Half of the team was using R. Some people were using MATLAB, and when I arrived, there was one researcher in my team using Python, and I was using Python. And so the reason I was using Python is I knew Python, I didn't know R. The reason why this other researcher was using Python was that he was doing bioimaging, so which involved fairly large data set, like 20 terabytes of images, and a lot of annotation. So he needed to be able to do a bit of web interface for biologists to annotate the images. And this is still quite hard to do with R. So there are solutions to interface R with other languages, like Python, but it's just so much easier to do everything in Python. 10 years ago, the situation of statistics in Python was quite hard, but around 5-6 years ago, a new package arrived, which is called Scikit-Learn, which is a package for statistical learning, which has all of the state-of-the-art tools of statistics, and that made it very easy for people like me who don't necessarily need the fancy new algorithms for their research to use to do statistical analysis and statistical learning in Python. So here I'm going to see how it evolves because of how R is big. So I think one of the advantages of Python versus R is now that we have massive data sets in biology, R sort of hits a limit in terms of what it's able to deal with. So some of my colleagues here had to switch to Python just because the matrices were so big, and R was not well adapted for this. So we'll see how it evolves in the next.
So maybe, Fernando, you probably have some of the best meta view of where Python sits with respect to R, and Julia and many other languages that are old school but also very cutting edge and perhaps created after Python and potentially one day going to supersede Python. Can you say a bit about why you've decided to become completely interoperable? Obviously, this started firmly IPython in the Python world, and now even just with the name change that involves JU for Julia and PY for Python and R at the end for R, you've clearly tried to make kind of a intellectual land grab over all of these different languages. How do you see all these things fitting together?
Yeah, so there's sort of two layers to that question. One is at the level of languages themselves and the ecosystem, the current state of the ecosystem of scientific computing and data science, and how Julia, Python, R, and potentially other tools play in that landscape. And then the second one is kind of at the level of Jupyter, so I'll try to quickly answer both. Languages-wise, I continue kind of doing my work in Python. It's the tool that I reach for first. I continue loving it. It hasn't stagnated. Python continues to evolve. 3.5 has introduced new tools even for scientists, like the matrix multiplication operator that will make sort of matrix-oriented linear algebra code a lot cleaner to read. 3.6 is coming out soon with a lot of features that are going to make it very appealing. Tools like Numba that Kyle just mentioned bring elements of performance into the language that were really not available 5 or 10 years ago without doing a lot of extra work by hand, and it's becoming very, very easy to squeeze a significant additional performance out of the language. So Python is not stagnant, but R and Julia in particular are two languages that continue to evolve. I'm not personally super fond of the R syntax, but R continues being the lingua franca of statistical research. And so if you really, really need a cutting-edge algorithm, if you're really interested in something that has been done very recently as a PhD thesis in statistics, chances are, not uniquely, but chances are it will have been done in R before it was done in Python. And there's a lot of good work being done in R. And Julia is a language that I'm actually personally super excited about. I think on the one hand, it brings healthy competition to Python because it does show that it's possible to build a modern, high-level, pleasant to use language using the both modern tooling like LLVM and the modern compilation machinery and modern ideas about type systems to make a very compelling environment. The jury is still out on what it will do for science, but I think it's very, very interesting and very exciting. And it complements Python very well because it can bring ideas, it can show it's a newer and more experimental playground where ideas can be tested with flexibility and bring them into Python. Today, Python, interestingly, is now a little bit of the old dog in this space, and it's obviously showing telling me about my own age, that when we started, we would go to conferences and we would have all these slides saying why Python for science, and yes, you can use it, and yes, it's okay, even if it has all these limitations. Now Python is sort of the established player in terms of high-level interactively capable languages for science, and something like Julia is now the up-and-coming one. What that means, I think, is that those languages now, like Julia, will have a harder time penetrating at large scale just because now the established weight of Python in the ecosystem, the interlocking of all of the libraries and tools that are available just makes it harder, right? There's a barrier to entry to new players, and between Python and R, that space is well occupied. But I think all three of these are worth learning. They're different languages, and it helps your brain to see problems from different perspectives, and they do bring kind of different types of value to problems in science. From the perspective of Jupyter, I think what happened was we realized that as we were building the protocols for interactive work and the first versions of the graphical console and then the notebook, it was very clear that basically 80% or 90% of what was there could in principle be done with any language, not just with Python. And for us, the intent of building a lot of those tools was really about collaboration in science, about archiving your scientific output. Today, a lot of our work is being done in these modes of operation. We want that to be something which you can read and find and share 10, 20, 30 years from now. We thought a lot about the data format, for example, of the notebook, to build it in a way that would make it easy and possible to share, to convert to other formats, to archive. And when you think of it that way, then the language is really irrelevant. Is science going to be done in Python in 20 years? I don't know, in Julia, in R, but the ideas that are captured there, I can read a paper in PostScript or PDF that was compiled with LaTeX 20 years ago, and I can still read the ideas in there. So it was really about building a tool for that layer, for the layer where we're capturing live computational knowledge, regardless of the domain, regardless of the discipline. And if we really wanted to take a stab at that question, we had to move past we are a tool for one language, which is, for example, what tools like Mathematica or the Maxima or the Maple notebooks, which had some of this, never really did. They always remained anchored in one language. And it took some work in tooling and abstraction, but I personally think it was the right thing to do.
So, Clarice, if you wouldn't mind passing down, we heard from Nelly that it sounded like there was a barrier to entry for her at some point, which was there's a whole bunch of great stuff happening in R, and as soon as Scikit-Learn came along, that whole sort of thing fell down. Is there something in your domain where it was just sort of silly to even think about using Python, and then all of a sudden a new package arrived, and now it made sense? Did you have to build that package? Maybe just talk about some of the barriers and why didn't it come earlier for you?
There are two things that I can add to that. First is that in my field, I do basically biological imaging. I don't have like terabyte-sized data sets, but I have gigabyte-sized data sets. And people usually use ImageJ to analyze the images. And basically in the past years, there have been like huge developments for ways to handle images with Python, right? So this has been helping me in my research. And another way to answer this question is the fact that, so I was a very heavy MATLAB user, and the Python thing clicked for me and for actually many people that I have worked and work with when we found a IDE. What does IDE stand for? Integrated.
Interactive development environment? Integrated. Yeah.
Integrated development environment that looked like and felt like MATLAB. For instance, I do most of my long computations either using Spider or PyCharm, right? And this, for me and for many people that I know, has helped a lot break the barrier. And another thing is that, in my experience, there is a lot of online help for Python and Python functions, and it's really easy to find help.
So how important is community for the other two of you? How often are you interacting with the community? And I know both of you are core contributors to some of the things that we use on a daily basis, so maybe talk about why you feel that it's in your interest to be contributing to the community.
So for me, the community really had a huge impact. I think I started using Python because of the language, but I stayed for the community, and I haven't moved to Julia because I love the community so much. So I'm a core contributor to Matplotlib and Scikit-Learn. I've learned most of what I know in Python by contributing to projects, an open source project where people already knew the language much better than I do and still do. I also think that the Python community, compared to other languages like Ruby, which is not used in science so much, but I used it as well in my company a while back. The Python community has a very strong, good practices, and that has influenced the way I do my research a lot. So, for example, testing is something that's really hard to do in C++. So when I was doing C++, I didn't do it. When I started using Python, I did it much more. And compared to Ruby, I would say the packages are more stable. The community is more careful. So the Python community helped me be a bit more careful about documentation, reproducibility, and things like this. So I don't think Python is a great language. It's old. It's now 25 years old. And it's moving still forward, but I don't think it's a great language, but I do think that the Python community is pretty awesome.
Is anybody here born after 1989? Okay, so Python is older than you. Fernando.
Yeah, the phrase that Nell used is a phrase that I've used myself, and we're not the only two people to have used it. I came for the language, but I stayed for the community. And I've actually heard, and I've said this myself as well, but I've heard multiple people say specifically about conferences, for example, like the SciPy conference, that they vastly prefer that space as an intellectual and scientific community to their own disciplinary spaces, because so much of the work we do in academic research is because of the incentive structure of authorship in papers and tenure track positions and PI status on grants and whatnot. So much of our culture in academic research is focused on effectively stomping on the heads of everybody around you so that you can stand above them and gain fame and fortune for what little fortune there may be in this space. And the SciPy, and this community, even though it is made of scientists, most of the people working in the space are grad students and postdocs and academic researchers, either at universities or at research labs, the NASA, Hubble Space Telescope, the national labs. There's a very different ethos. People seem to come to these spaces and actually find it in themselves to work together, to collaborate, to share in a very genuinely open and generous fashion what they do, and also do things that, as Nell hinted at in her comments, I think in many ways represent the ideals of science better than even science does. So the ideals that science is something that is built together for the common good in a way that validates its results, in a way that shares its problems openly, in a way that is reproducible. All of these ideas are in many ways encoded in the common practices of these communities by having your bugs up on GitHub, by having your test suites up on GitHub, by sharing your code and your data. All of these things are actually supposedly the ideas of what the scientific enterprise was, but so much of that has been lost in the underbelly of the professional incentive structure of science. And so in that regard, I do find the community extraordinarily important, and a community that I find a much more rewarding one to contribute to, because I get a lot more of it back. As Nell said, I've learned a lot. I've made extraordinarily personal friendships in this space, and partnerships that are both technical and intellectual that have run for now 15 years and counting.
Yeah, I mean, in fairness, of course, it's not a nirvana, this community, right? It's still got its problems.
It's not perfect.
We had some pretty open discussions about how poor it was from an underrepresented group perspective of the number of presenters at the last SciPy conference, right? There were a number of people noting that there were not a lot of women giving talks. So just like in many other communities, we still have issues and we still have things to be working on. But I think I'm hearing all of you say, and I'm seeing nods, that this is still a fairly welcoming community, and that's one of the reasons why you stayed.
Yeah, no, I certainly don't want to brush those problems under the rug, because they exist and they're real. Some of them are evidence of similar problems that also exist in academia. Others are unique to this space, and so no large enough group of humans is perfect, and I wasn't trying to claim that. But I have found some very valuable things in this space.
So before we turn it over to questions, maybe I can ask a somewhat provocative one of, what do you hate about Python? What would you love to change? And I'll leave that open-ended. You have to say something, though.
It has improved a lot recently, but it used to be extremely hard to install packages. And so both in terms for the scientific community, because we have a lot of code that relies on Fortran and C code, but also in the web development world, it used to be extremely hard to have environments set up in a way that things would work. And when you have to spend a week figuring out what to install and breaking your OS because, well, at the time I didn't really understand what I was doing, that was very, very painful. So, but it has become much more easier recently.
I'll hold one plus for that. And yeah, installing packages sometimes is a bit, you have to Google sometimes for dependencies, and sometimes what you use in using, for instance, pip install is different from what you use using conda, or you have to do sometimes a lot of Googling. And what I hated was I had some code written in Python 2 and I had to migrate it to Python 3. And it was a lot of correcting it.
Renato?
For me, I think the fact that traditionally performance hasn't been seen as a real problem and by the core team. So we, when I say we, the scientific Python people, sort of the people who care about NumPy, SciPy, Matplotlib, et cetera, right? We gain a lot from building on top of a language where there's a core team that builds the language itself and the tooling around it. And when we need a web tool, somebody else built a great web server and we don't have to. So there's a huge amount of benefit from that we gain from that. But it also means that to some extent we're limited in what influence we can have on the core language. And the core Python team for a very long time hasn't really treated performance problems as a problem. They're kind of dismissive of that. Often they said it's fast enough, or if you need it to be faster, just write it in C, and that I think is, in our space, that's not true. If you have to rewrite it in C, that barrier is a high barrier. If you have to drop into another language, that is a problem. The fact that doing parallel computing in Python is not as seamless and transparent as it could be because of the global interpreter lock, it's a real problem. It's a hard one to solve, but it has been there for 20 years, for crying out loud. And so the fact that these problems are not taken more seriously kind of annoys me. We're getting more and more hooks into the language, actually, to let us work on that. So the new machinery for function, for type annotations, for example, starts giving us some of the information that then tools like Numba or Python can pick up on to produce different performance characteristics. And so there's ways out, but I wish they took that problem more seriously.
All right, well, let me open up for questions to the audience here. Anyone have any questions for our panelists? Yes.
I see the comments that you have
Can you just repeat the question?
So he wants to know that in our academic environment, usually, for instance, MATLAB licenses are available, mathematical licenses are available. Why would we make the effort, invest some time, and switch? So if you allow me, I'll start my answer with an anecdote from a friend of mine who went into industry. He actually was a MATLAB user, right? And the problem when he got to his industry job is that his company did have a MATLAB license, but what it took him some time to find out is that all the packages that we're used to here at the university, they weren't necessarily included in the company's license, right? So every time he needed a package for a function that he was used to using while he was a student, he would need to ask the company to buy the license for this extra package. And the problem was not that the company wouldn't buy, the company would buy, but just the time that it would take for the billing department to go to MathWorks and buy the freaking package. So he was like, no, this cannot go on. I'll have to switch to Python. So he switched to Python in an industry position. So why not start the switch before, right? But I don't know. For me, I think the main point was that it was actually open source, because I was getting annoyed about things that I couldn't understand or control too much using MATLAB and Mathematica. And it was, I saw my transition as sort of an investment, that I needed to invest this in my future, in what I believed that I should do to myself, and whatever it is that I'll do in my next job, what I would like to enforce to people I work with.
So I'll just add something. I don't know how it is here at UC Berkeley, but I know that at least at the University of Washington and in my university in France, it's not because you have a MATLAB license that it's free. And a friend of mine recently realized that his lab was spending 40,000 euros per year in MATLAB license. Because they had a lot of users, but with 40,000 euros in France, you can not hire someone for 6 months, right? So at some point, he just realized that maybe it was time to switch to something else.
Maybe if I can add a couple of additional points. The first one is that by virtue of using open tools, you can collaborate with others without a barrier, and that other can be your colleague at an institution who doesn't have access to that, and the scientific community is made of people from very many diverse backgrounds. For me, that wasn't important. I wasn't using MATLAB, I was using IDL, but the argument still applies. I come from Colombia. It's a country that can't afford these proprietary licenses, are very expensive. If I wanted to be able to collaborate with my colleagues from a country like mine, using open tools was basically a precondition to that. That other person could be yourself, as Clarice's colleague, yourself later, in a different environment where you don't have access to these resources. But even in academia, in addition to what Nell said, I remember an anecdote from a colleague of Josh's, who used to be a grad student at UCSB in computer science, and who eventually got kicked out and banned from the campus cluster because he was running computations in batch mode in parallel and using up all the licenses they had. And it turns out that they actually kicked him out of the cluster because he was consuming all the licenses, whereas the Python licenses, they all cost the same. Whatever number you multiply by 0 is still 0.
Yeah, I just say, from an educator perspective, one of the reasons why I started the boot camp is because I saw all of my students and all my colleagues using proprietary code bases like IDL, and given all the issues we had around costs and reproducibility, and then understanding what's deeply inside the code from a scientific perspective, I realized that unless we were teaching our students Python, we were doing them a disservice, not just for the time that they were here at the university, but many of them obviously won't stay in academia where they'd have the benefit of getting a license that's effectively free for them, but many of them would be going into industry and setting them up to basically join industry where all they know is an IDL or a MATLAB, I think put them at a severe disadvantage. We had another question in that general vicinity. Yeah.
So you mentioned about the yield block as being an impediment in terms of parallel processing. What sort of advice do you have for people who are needing to do parallel processing within Python
So I'll just repeat the question. Fernando brought up the dreaded GIL, the global interpreter lock, which is something that I deftly avoided mention of until just now. So how does one think about doing parallel processing given this fairly fundamental limitation? And I think maybe we'll just ask Fernando to talk about parallel computing.
So the issue, just for context, is that the Python interpreter has a lock, the global interpreter lock, that protects, even though Python supports multiple threads and it has a really good threading library, that threading library can only run one thread at a time that touches the state of the interpreter itself. So if a thread is waiting for network data, if a thread is waiting for some other resource, they can run fine, and that's typically how it's used. But no more than one thread at a time can modify the state of the interpreter. No variables that are visible to the interpreter can be modified. And that is a serious limitation for certain classes of workloads. And so the alternatives you have are either to work sort of under the GIL or above the GIL, because you can't really get through it. Under the GIL means you work in C, you pre-allocate data structures, you pre-allocate working space, and then in C or in Fortran, when you enter that function, all of the work can be multi-threaded, but it's basically work that is opaque to Python. Python is stopped and waiting for C to return. And NumPy, for example, can be linked against the Intel math kernel library or against the multi-threaded build of Atlas so that you get the linear algebra routines to run in multi-threaded mode. And so that is kind of going under the GIL. The other alternative is to go over the GIL, which is to work in multiple processes. And there's a variety of tools to make it easier to distribute work across multiple Python workers. Python itself ships with a module called multiprocessing that does a perfectly competent job for certain classes of workloads. And then there are sort of high-level libraries that have been built to ease certain patterns that are common in scientific computing. Scikit-Learn ships with one library called JobLib that helps you parallelize and distribute certain classes of workloads. IPython actually has a library for interactive distributed computing called IPyParallel that is especially focused on sort of the interactively controlling clusters of nodes, given kind of the spirit of IPython. And there's sort of a new entrant in this space in the last, year and a half maybe, Dask?
Oh, Dask, yeah.
A year and a half or so maybe, called Dask, D-A-S-K, which is a really nicely thought out library developed by an engineer at Continuum, but it's fully open source, for basically distributing DAGs, distributing graphs of computations over resources. And it has a lot, the API is very elegant and it has a lot of facilities for debugging, for monitoring jobs, for whatnot. It's a very elegant piece of work. The author is called Matt Rocklin and he's very responsive. We're using it in several projects. So there are a few tools in that space, but the GIL is a reality of our universe.
Any other questions? Okay, so the question is about if somebody can compare Python in the context of web development. We've been mostly focused on sort of research-oriented workloads. I don't know if any of you have experience there. Yeah.
So a very long time ago, I used a bit, so I used to do web development, and I used a couple of frameworks. So I used Ruby on Rails, which is why I have experience with Ruby. I used a framework called Symfony, which is a PHP framework. That was the worst experience ever. And then I did a bit of web development in Python. So in Python, you have a very large choice of web development, some which are quite close to Ruby on Rails, and some which are very light and more flexible. So while I enjoyed working with Ruby on Rails, I think it may have improved now because this was 8 years ago. It was really hard to maintain because the Ruby community has sort of a habit of breaking backward compatibility. So you use one version of the software, you update, and then you need to spend a month upgrading your code, which may be fine if you work in a software engineering team and you have 10 people working on it, but when you're doing research, it's a bit annoying. Now, this also happens in Python. The reason why I mention how hard it was to install a project is in Python, you need something to deal with the database, and you need your web framework, and you just have like 10 libraries that you need to use, and at some point, one of them is going to break backward compatibility, so you need to spend quite a lot of time also fixing this, but it's not as bad as with Ruby. And when I did my PhD, some people were using Perl as well to do web development. They seemed happy about it, just that you need to implement a lot of the things that you wish would be easy. So I don't know if this answers your question.
That's a question over there.
Just bringing up probably stupid questions, but one from Silicon Valley, you know, the series on HBO. I don't know if anybody follows it, but there was this big discussion about tab versus four spaces.
Yeah.
And I want to bring up the other thing, one of the links that you gave in your original thing, Python versus Perl,
Yeah.
the big debate.
Yes.
Can you talk about it?
Okay, so for people who don't know Perl, compared to Python, so Python indentation means something. So you are forced to indent your code properly. Perl is exactly the opposite. You can do a whole program into one line. It's unreadable, but it's going to work. So it's a very different philosophy. Perl people absolutely usually hate Python and vice versa, so I think it's also a question of what you like. I personally don't mind to have to be careful about indentation. I think it makes my code really easy to read, so I prefer this. And then I have some friends who are like, but this breaks your creativity, which, okay, that's not my point of view, but some people feel this way. Now, the tab versus space issue, it's an interesting one. So a very, very, very long time ago, during my studies, I had to contribute to OpenOffice, which was now renamed LibreOffice. And it was a very interesting experience. So the code is written in C++, so indentation doesn't mean anything. So we opened naively the file we were supposed to modify. And it turns out that it was a mixture of tabs, spaces, and then people obviously had converted tabs to space, but sometimes it was to 4 space, sometimes to 8 space. So basically the code was not indentated properly. And that's a major problem with tabs. So someone can visualize it as 4 spaces or 8 spaces, and if someone else edits the file with space, then you can end up with a file that's not indented properly. So I don't mind the fact that Python imposes either spaces or tab. Mixing them is just a bad idea in general, because you don't know what's going to end up being just in terms of formatting. Now, I know that for beginners, this is a huge hassle, and this is something that's underestimated by people who teach Python, that these are characters you do not really see, so it is a huge hassle for beginners to deal with this problem. And having a text editor that does this properly is not something that comes out of a box very often, so that means configuring your editor.
One quick thing to note on that, though. I'm pretty sure that Python 3 actually now refuses to run code if it has mixed tabs and spaces. It used to be a warning. I think now it flat out refuses. They've basically said, okay, enough with this. Let's just make it a hard call. So I'm pretty sure that Python 3 actually refuses to.
I think Python 2 as well, but it's just really confusing as a beginner. When you try, your code is indented properly, you run it, and then it spits out an error message you don't understand. It's just really annoying.
All right, so I think what we'll do is wrap up. Let's give a round of applause to our panelists. Thank you. And what we'll do now is just I'll give kind of a wrap-up lecture, and then we'll call it quits.